All right, so this is the meeting for the Unit 3 mini test for ESSC 102. This is our last exam before the final. So it might be worth mentioning that the final is Unit 3 only. So it's just going to be just like any of the other unit exams, and it's worth the same as any of the other unit exams. This mini test will just be on lectures 17 through 20. So it's all that information about light and a little bit of the preliminary information about stars and our star, the sun. So what I'm going to do is my usual share screen thing, get that started, and then I'll take you on a little Moodle tour. You see the infinity loop we get stuck in every time we do this, all the good things. So first, while I'm doing the share screen, I wanted to show you, here's the Moodle page. I already pulled up Unit 3 for the class. Both of these sections, I know this might not be your section if you're in Section 2, but they should be pretty much identical. The big picture for this unit, the one I kind of wanted to headline, was the basic concept of the HR diagram. That's how we classify stars on spectral type as a proxy for temperature and luminosity. And then we're doing lectures 17, 18, 19, and 20. 17 and 18 are effectively lectures on light. 19 is on the sun, and then 20 is on classifying stars, which we can do when we start with the sun so that we can classify other stars in comparison to the sun. Then the mini test is on that stuff, and then I save the best stuff for last. So all the black holes, neutron stars, birth and death of the universe, big picture kind of stuff, that's all the second half of Unit 3. So this is where the recording will be once I get it all posted. I'm going to go through at least a few of these review questions, and I've already pulled up the Word document over here. So questions 1 through 4 pertain to stuff that's covered on the mini test, with effectively just one question for each of the lectures 17, 18, 19, and 20. And then the rest of the questions are stuff from 21 through 24. So when we review for the final, we'll go through those. So check back in the meeting real quick to make sure I didn't miss anything. But if you guys don't have any questions for now, I will go ahead and get started with those review questions, starting with the one from lecture 17. It deals with information that can be determined by light. So first off, there's a lot of stuff that's part of this lecture on light that leads up to the determination of information from light. And that's the whole idea that light or visible light is part of a broader spectrum. We can take light and divide it into its components by passing it through a prism. That's when we get an object spectrum, or at least the visible light portion of the spectrum. There are different types of spectra, being a continuous spectra, emission line, and absorption line. I don't plan on asking a whole bunch of really detailed questions about that, but it's pertinent because some of this information relies on these different types of spectra. So that all leads up to the second half of this lecture where I really kind of go over in more detail information that can be determined by light. Because light, and I'm actually going to go ahead and write this down because it's so important, light is our only source of information for distant objects. And astronomically speaking, I'm using distant to mean things outside of our own solar system. So we can't send a probe. We particularly can't send astronauts to these really, really super distant things that are going on outside of our own solar system, distant stars, distant galaxies. So all we have to go off of is the little tiny bit of light that we get from these objects, but we can glean a great deal of information from that light. The information that we can determine from that light basically boils down to 1, composition, 2, temperature, 3, motion, or specifically the aspect of the motion towards or away from us. Now I'm going to give you a very sort of brief overview of how we get this information. First, with composition, we have to look at the details within an object spectrum and look at the placement of those emission and absorption lines. Emission lines are basically the bright lines of light in an otherwise dark spectrum. The absorption lines are basically the opposite, little bits of blacked out part in an otherwise continuous spectrum. The placement of those emission and absorption lines indicates to us the presence of certain elements in this distant object. So elements leave a fingerprint of sorts in an object's spectrum as certain emission and absorption lines. So the object's spectrum indicates the presence of certain elements. So not only do we know a little bit about the composition of distant objects from the spectra, we know about the relative abundance of some elements versus others in the universe, based on what kind of spectra we see from these distant objects. So hydrogen and helium are super abundant in the universe. Most of stars are composed of hydrogen and maybe a little helium. And then everything else is relatively really low abundance. But we can see what's there chemically through the object spectrum. Now this it gets a little bit complicated, and I only really cover the most basic sense of how we determine composition from astrophysics. It gets a little bit more complicated than that, but if you want to get into nitty-gritty details that you will not be tested on, episode 5 of what they call sort of, well, let's call it Cosmos. What's the two? Well, let's go say Cosmos 2014. The Cosmic Perspective. I'm trying to remember what the tagline of the first Neil deGrasse Tyson Cosmos was now, and I'm forgetting. Oh, A Space-Time Odyssey. That's what they called it. If you're into it, you want to go back and watch episode 5. If you watch the entire thing, they go into this idea of exactly why certain elements leave their chemical fingerprint in spectra in a lot more detail. Also, it's just done in a really cool and extremely entertaining way because it's Neil deGrasse Tyson. So it's very entertaining, very watchable. It's much less dry than the a normal sort of show that would be sort of similar to that, kind of that same narrative way. Now that I'm talking about this, it might be a useful point to mention that from here on out, a lot of what we covered is also in at least one of the seasons of Cosmos. You notice, like in the videos, I use a lot of little clips from Cosmos because it's just done so well. But there are some episodes in particular that are really useful to go back to. And I'll kind of put that in the notes here so that if you want an additional source of information to really maybe kind of put it in a different way, kind of help you absorb some of these concepts, then you can always go back and watch those. This is certainly not the only source for this information. It's just, sort of another way of getting at it. Let me go let someone in real quick. Here we go. And come back over here to the review. So we're on question 1. What information can be determined by light? Because light is our only source. The first piece of information is composition. The second one is temperature, which is revealed by an object's spectrum. We'll even say spectral type and color. Now, when I'm talking about temperature in the lecture, I go into Ven's law. you will not be using Ven's law. And really, if you get the basic concept that the redder, longer wavelength end of the spectrum typically represents cooler things, and then the bluer, shorter wavelength end of the spectrum represents hotter things, as long as you get that basic concept, you don't really need Ven's law. If you're not actually doing the math, and we're not, then you don't really need to know that. I just kind of wanted to throw that in there as be a little bit of a source for that information. So temperature is definitely something that relates strongly to an object spectrum. Where that object spectrum peaks, that gives you an indication of its temperature. So if it peaks out in the longer wavelength end of the spectrum, typically it's a cooler object. Shorter wavelength, bluer end of the spectrum, typically it's a hotter object. And that's certainly true for stars. So we could even take this a step further, and in later lectures, I'd start talking about how an object spectral type is related to temperature, and we get into the origin of the 7 spectral types. There's a Cosmos episode for that too. So I think once I get into question 4, I'll reference that, and I'll give you a Cosmos episode. Again, if you want to go back to it, it's not totally necessary, but it helps. So temperature is revealed by the object spectrum via the spectral type, the OB, AF, GKM. We'll get into that in a minute, and the object's color a little bit more simply. The last aspect of an object, the last piece of information that is determined from light or can be determined from light, is whether the object is moving towards us or away from us. And it's based on how the motion of the object affects the object spectrum. So to make this work, you need something to compare it back to, at least some sort of estimate of what the object would look like if it was stationary. But we can tell whether objects are moving towards us, away from us, based on something called the Doppler effect. So effectively for us, what this means is that objects moving towards us are what we call blue shifted, where the entire spectrum and the emission and absorption lines are shifted towards the blue end of the spectrum. So that means they're shortened, basically. It's kind of like as the object's moving towards us, that tension that would sort of be on like an imaginary spring would be relaxed or tightened somewhat as the object is almost pushing those wavelengths of light closer to us. So that's why it's shorter wavelength, blue end of the spectrum. Objects moving away from us, and the example I give that's really pertinent is the red-shifted galaxies in an expanding universe. Objects moving away from us are red-shifted. Or, in other words, all of those different wavelengths of light are almost sort of stretched outwards. And the bigger the difference in the more the increase in the wavelength, the closer you are to the red end of the visible light spectrum. So therefore, it's red shifted. So this is all of the information, very, very simplistically put, that you can determine from light and that we use to further understand stars and objects in distant solar systems where light is the only source of information. What is the object made of? Its composition. What is the temperature of the object? And then whether the object is moving towards us or away from us. So let me stop for a second, go back to the meat and see if I missed any questions. Okay, will any of the info determined by light change in our lifetime in a significant way? That's a super loaded question because as a scientist, I'm supposed to say, absolutely, any of this can change. Now, there's the cutting edge of science where things are constantly changing. And then there's science in a general education class like this, where this has been in effect for over 100 years. We've known a lot of this information. So it's not likely to change. What is likely to change is maybe with new technology, like with the launch of the James Webb Telescope. Will we be able to get even better information that changes our perception of the universe? Absolutely. So that was a yes, no kind of answer. I know that was kind of dodgy, but as far as the general concepts go that I cover, very unlikely to change, but it could. Hope that answered it in some sort of wishy-washy way. Okay, so going back to the review here, I'm going to go into question 2 now. Describe relationship. I'm sorry, grammar fail. Describe the relationship between distance and time as it pertains to this question. I love all of the various incarnations of this question that you can come up with. And I always try to target some specific time in Earth history, like the creationist version of how old the Earth is, or when the dinosaurs went extinct, or something to that effect, so that you can get a little bit of a sense of how the relationship between distance and time affects our perception of the universe. To understand this question, you need to understand first that when we look out into space, we effectively time travel, because light has to travel incredible, unbelievable distances to us. So this changes our perception of the universe, because we're seeing things as they were and not as they currently are. Now, I kind of just picked on something specific that's relatively close to us, but you could use any kind of version of this question to get at the same understanding. So I picked on this Eagle Nebula, which is fairly close to us in the Milky Way galaxy, and it contains the famed pillars of creation. Really quickly, I'm just so you have an idea of what this looks like. I'm going to just kind of pull this up real quick so you can see the pillars of creation. Here they are. This is at least the Hubble's version of the pillars of creation. So this is a beautiful nebula, only about 6,500 light years away from us. So light traveling at 300,000 kilometers per second from the stars that are being birthed in this nebula. That light began at those objects and started traveling our way 6,500 years ago. So that's how long the time delay is, in a sense. So now that we have the background for that, describe the relationship between distance and time as it pertains to this question. The pillars of creation is located 6,500 light years from Earth. If Earth were only 6,000 years old, would we be able to see the nebula at all? Why or why not? So for the context of this question, we're pretending to be like young Earth creationists, right? That believe that the Earth is only 6,000 years old. Would we still be able to see it? So effectively, to understand this question, we need to think about it from the idea that whether Earth was here or not, light began to travel from this object 6,500 light years from Earth, 6,500 years ago. So in this context, if Earth were only 6,000 years old, but the universe was much older, it would still be possible to see the pillars of creation. So effectively, that light would have left those objects 6,500 years ago and spent the last 6,500 years traveling from that point to us. So no matter how old the Earth is, we would still be able to see it. Now, if, big capital letters here, if the entire universe were only 6,000 years old, we would not be able to see the pillars of creation, because enough time would not have passed for the light to travel to us from those stars. So there's lots of different ways we can get at the same information, but the basic concept is any view of space, no matter how close we are to that object, even if we're talking about the moon or the sun, there always is going to be some level of time delay. For the moon, it's seconds. For the sun, it's minutes. To even the nearest star, it's going to be a time delay of years between when the light left that object and when it reached us. And when you get to the things that are furthest away in the universe, you're going all the way back to the beginning of the universe itself. So there's this visible boundary of the universe where we can't see past that because we're looking past it to a point before the universe began. So it gets basically really, really weird, really trippy. And another thing that definitely helps understand this concept is going back to another Cosmos episode. This is same season of Cosmos, the 2014 version of Cosmos. I believe it's episode 4. The name of the episode is called "A Sky Full of Ghosts," and it's kind of they use this relationship between William Herschel and his father explaining some of these concepts to him as a young boy, to basically just break your heart and make you cry and marvel at the universe. It's a magical thing. It's definitely fun to go back and watch. I do use part of this in lecture 18, but mainly that part where they're talking about the time delay between relatively close objects and then getting further and further away to objects in the galaxy and beyond to distant galaxies. So it's a fun thing to go back and talk about. Let me check in with, where'd it go? The chat here, make sure I didn't lose anything. Okay, so the question was, so it's basically depending on the time it takes for light to travel and the distance it has to travel. That is correct. Yeah, so the closer an object is to us, the shorter the time delay and the more recent, in a sense, our understanding of that object is. When you're talking about stars that are hundreds of thousands or even millions of years away, it's possible those stars aren't even there anymore. And we're really almost just looking at the memory of those stars. So that's why the name of that episode was called "A Sky Full of Ghosts." Okay, so you're so welcome. I'm going to go back to question 3 now. This one is all about the sun. So for just the context of this one question, we kind of go back to the solar system. Even though most of this unit is talking about things outside of our solar system, it's nice to be able to go back to our solar system because our sun is the best proxy for us to be able to understand other stars because we basically live right on top of it. So the question is, what process allows the sun to create light and heat? Describe how the sun is able to self-regulate its internal temperature to sustain the creation of light and heat. And the process that's being discussed here is called fusion. So there are 2 nuclear processes that both create a tremendous amount of energy. Fusion is the process of taking small particles like the nuclei of hydrogen atoms or helium, something else that's relatively small, and slamming them together at high enough temperatures, pressures, and speeds to force them past their repulsive tendencies that the electrons provide and to have them just glue together and become one. They fuse together. The opposite of that would be fission. So when we talk about splitting the atom, creating energy from plutonium, uranium, etc., that's fission. It typically produces less energy than fusion reactions. But in order for most forms of fusion, at least that we know of, to take place, you have to have absurdly high temperatures. And that's why we can't manufacture this process and harness it on our own. That's why people talk about cold fusion as this, thing that might be possible for later generations as a process that would allow us to create lots of energy and save the planet at the same time. But we can't do it yet without expending more energy than we would create, thus kind of invalidating it as an energy form, energy source. So fusion is the process that is causing the sun to create light and heat. So specifically, What the sun is doing is converting 600 million tons of hydrogen into 596 million tons of helium every second of every day for the last 4.5 billion years and for another 5 billion years to come. And light and heat is just the energy that's created as a byproduct of that reaction. That's the E part of E equals mc squared. So this is specifically, specifically, I guess I didn't pronounce it right, so I couldn't spell it right for a second there. Specifically, hydrogen fusion using the proton-proton chain. Now, the proton-proton chain is just how low-mass stars like our sun undergo hydrogen fusion. It's effectively the opposite of how high-mass stars do it using something called the CNO cycle. For this part and for this test coming up this week, it's not really necessary to get too far into the nitty-gritty of the proton-proton chain, nor is it going to be necessary at any point to be able to name the individual parts of that reaction. For our purposes, 4 hydrogen go in, 1 helium comes out. And as a byproduct, you create light and heat. That's like our necessary level of understanding of this. So what happens is that gravitational collapse creates heat and pressure in the center of our star that allows fusion to take place. And fusion creates an outwards pressure. These two forces work in opposition to each other and regulate each other. So, i.e., as long as gravity is pushing inwards, then it keeps the temperature up. And as long as the temperature is up, fusion will still take place at the same rate. If fusion gets really crazy all of a sudden, starts to produce a lot more light and heat, then the star would actually expand. And then that would cause gravity to fight back again and push back in. So this is called gravitational equilibrium, where gravity and fusion are working opposite of one another. And as long as one of them doesn't get too far and outweigh the other, the star is in equilibrium. And then if it's equilibrium equal, then that means that it's going to keep undergoing fusion at the same rate as long as it can do that. Now, it's after the star runs out of hydrogen, and our star will run out of hydrogen in another 5 billion years. We'll all be way dead at that point, so we're in good shape there. After 5 billion years, after the star runs out of hydrogen, then it has to do some other weird things to kind of keep that balance in check. So this basically answers our question number 3 here, which is sort of our first taste of the details involved in fusion and how low mass stars undergo fusion. The other part of lecture 19, the sun, that's important to take away is the part of that lecture where we talk a little bit about space weather. And so I show a lot of pictures, but really it all just boils down to the magnetic field and its relationship with the photosphere. And the last thing that I wanted to take away from lecture 19 is that the whole part about the structure of the sun gets probably kind of dauntingly wordy. You probably are kind of going through that part of the lecture going, how am I going to remember the difference between the chromosphere and the photosphere and the radiation zone? And there's just too many different layers. So focus on these. These are the ones that could potentially show up on the test. The core. The core is important because this is where fusion's taking place. It's effectively the heart of a star. The photosphere. That is the visible surface of the sun. That gives it its color. We have a yellow star, a yellow sun, because the temperature at the photosphere is, think about 5,300 degrees. And then the last part that you need to remember is the solar wind. The solar wind is what's going to lead to a lot of the space weather on Earth. So if you've got these three down, then I wouldn't spend a whole lot of time and energy trying to memorize convection zone, radiation zone, corona, etc. So coming back over to the meet real quick, make sure it looks like everything's cool over here and nobody has any questions. Questions are always welcome, but as long as there are no questions, I'm going to come back over here and dive into our last question that's pertinent to this mini test. 5, 6, 7, and 8 are all going to be on the final, along with the information from 1 through 4, but we'll cover that in a review session to come. So the question 4 is dealing with classifying all stars and doing so comparing them to our star. So what is it about our star that it's going to be different than another star? How can we use that to get an understanding and to be able to classify them? Describe in detail the 3 most important criteria for classifying stars and how this information is obtained. Of the 3 classification criteria, which determines the star's overall lifespan and is the most important? I'm forgetting to put the and a bunch of stuff, and it's starting to bug me. So the 3 components that I boil everything down to is effectively luminosity, temperature, and put a star next to the extra special, super important one, mass. So luminosity is a measure of the true amount of power a star radiates, the true amount of light that it creates in comparison to another star at the same distance. So effectively what this means is that a star may appear to be brighter or less bright depending on your position and your distance to that star, but when you're measuring them more on a fair playing field, apples to apples, 2 stars might actually have the same overall true brightness. So this another way of putting this is maybe true power or brightness regardless of distance. So this is different than apparent brightness. So from our vantage point on Earth, we have stars that are brighter or less bright to us, but it's a function of how close we are to those objects. The sun looks unfathomably, ridiculously bright compared to any other star in the sky because we live right on top of it. You know, if you lived your whole life right on top of a light bulb, nothing else would be able to really compare to that light bulb. But we know that stars in the sky are much, much, much brighter than any light bulb. They're just a lot further away. So luminosity is an apples to apples comparison of true brightness. Temperature is going to be determined by color and spectral type. And while I'm at it, you definitely do need to know the 7 spectral types. I don't ask you to memorize a whole lot. I try not to fixate on, you know, memorize this set of numbers and this set of percentages and so on. But in order to really have a unit where we talk about stars at all, you have to understand spectral type. But it's got handy mnemonic devices to ease that. So O, B, A, fine, girl or guy. It works both ways. Kiss me. O, B, A, F, G, K, M. And so spectral type, how continuous the object spectrum is, where the placements of those emission and absorption lines are, effectively boil down to these 7 spectral types. So all stars can be classified according to spectral type, subcategorized in that spectral type on a 1 to 10 scale, and then we can compare stars to one another in terms of mainly their temperature. So our star is a G2 type star, so that would make it partway between G and F. So that means there are B type stars that are way brighter, M type stars that are way dimmer. So O is the hottest, M is the coolest. And if you get interested in the history of the discovery of the spectral types and how we first started to realize that these object spectra actually then related to temperature and we could classify them that way, there is a Cosmos episode for that. So that's where Cosmos, again, 2014. I like the more recent version of Cosmos. It just doesn't have as much direct utility in the lectures. I believe it was episode 8. Okay, I'm going to Google it real quick. Give me just a sec. Sorry. Episode 8. Yeah. It was a really cool episode called Sisters of the Sun, where they talk about the women of Harvard in the 19-teens and the 1920s who really did most of the work and deserve most of the credit for our founding of the understanding of spectral type. I'm sure it's probably an episode of Mighty Girl too. So, but it's a cool episode. So luminosity is true brightness. Temperature is determined by spectral type. If you plot one against the other, you come up with something called an HR diagram. Where a star is in its lifetime is going to direct where it falls on the diagram, but stars that are in the main sequence part of their lifespan fall along the famed main sequence that runs down the middle of that diagram. And all is very much dependent on mass. Mass is the most important criteria which controls all of the other criteria in a star, like luminosity and temperature. So in other words, a high mass star is going to be both brighter and hotter than a low mass star. So ultimately it's all coming back to mass, but the caveat here, but mass is very difficult to directly measure. Only in cases where you can see how an object orbits around a star can you directly determine mass. And for example, binary star systems are really good about this. So in a binary star system, you can see how two stars are orbiting around a common center of mass and their relationship to each other, the distance between them, how long it takes them to orbit around each other and to complete that dance, tells us about the mass of either object. And so we can then use that as a direct way to measure mass and not kind of a roundabout way to measure mass, like measuring it through luminosity or temperature. So, but again, that's rare. Not all star systems are binary. Our star system is not binary. And so you would need a way to measure an object's orbit and the orbital properties to directly determine something like our star's mass. Because we have planets in our solar system that are orbiting around the sun and we can look at those properties, we can directly determine the mass of our sun. But it's just not going to be something that's always achievable. So that's question 4, and the last of these review questions. I'm going to come back to the review itself. Oh, okay. We got something really cool loaded question. I love this already. So is this where the theory of time travel comes from, that we see stars that have died? When is a star at its hottest, at the beginning or end of its life? And finally, I remember you talking about how stars can sort of revive each other. Could that happen with our sun? Oh, there's a bunch of questions here. Okay, I'm going to do these one at a time. The theory of time travel wouldn't really directly pertain to this idea that we're seeing things as they were and not so much how they are. It's just sort of a byproduct of how light travels across a great deal of space, and the speed of light is finite. The idea of just being able to travel through time is just a really fun niche in sci-fi. That's just fascinating to talk about. Like, if you could travel through time, what are the other effects to surroundings around us? The only direct relationship between astronomy and time travel that I've been able to see deals with the idea that really massive small objects like black holes warp the fabric of space and time to such a degree that depending on your placement next to one of these objects, you would be experiencing time in a very different way. And so that's where the more sort of sci-fi fictional version of black holes being used as vortexes through the fabric of space and time to show up at a different point in time, where that all comes from. The second part of this question, when is a star at its hottest, at the beginning or end of its life? Let me think about that. Throughout the main sequence lifespan of a star like our sun, it maintains a pretty constant temperature. I think it probably would decrease in temperature just a little bit over that lifespan, but it remains pretty steady, and that's why it's stable. At the end of its life, it actually expands. And so at least in terms of its surface temperature, it would cool down. Its core temperature would heat up. So in a sense, that's when it would be at the hottest point of its life. And then finally, when a star is at the very, very end of its life and it goes through effectively these death throes where it explodes and implodes at the same time, that would probably be the single hottest point in its life. Last question here. I remember you talking about how stars can sort of revive each other. Could that happen with our sun? That is a particular phenomena when you have two stars in a solar system, when you have a binary star system. And to my knowledge, it's not possible outside of those constraints. So we couldn't really kickstart our sun in the same way because we don't have another star. But if you have two stars in a solar system and one of them dies out and the other one's still going, under certain circumstances, if the space between those two objects is close enough, I'm thinking if probably that dying star is still hot enough, it can actually siphon off hydrogen and helium from the still living star and sort of kick itself back into motion. I think I probably referred to something kind of fun like a zombie star, but that's called a nova. So yeah, like I said, not possible with our sun because you need two stars in a solar system to be able to do that. Or in some cases, you have even more than two stars. You have potentially even three stars in a solar system. So, okay, with that, I think we're done with the material for the mini test. So again, that's lectures 17, 18, 19, and 20. Then we'll take the mini test, and then the rest of the semester is just about getting by those last 4 lectures, and you won't be directly tested on anything from previous lectures again. So, okay, just to clarify, our Unit 3 exam, which is our final, will not be taken on finals week. It will be taken the week before, correct? I'm pretty sure. I need to be looking at the schedule to be able to tell, but if it's on the schedule, that's the way we're planning on doing it. If I find that's really inconvenient for people and they would actually rather we wait until finals week, that's certainly something we could explore. Maybe you guys could give me some feedback on that, or I could consult the group chat about it. But I think if most people want to go ahead and take it the week before, we'll probably take it then. Cool. Okay. So with that, I'm going to go ahead and stop the recording, but stay with me for a sec.